It's London, 1928. A scatterbrained scientist returns from vacation to his cluttered lab at St. Mary's Hospital, where his petri dishes full of bacteria have been left unattended. His name? Alexander Fleming. Dr. Fleming scanned the dishes, only to notice something alarming. One of them had been contaminated by mold, a careless mistake, or so it seemed. But rather than toss it aside, he decided to take a closer look. What he saw next shocked him. Around the mold, the bacteria had stopped growing. Was it a fluke? A mistake? Fleming didn't know it yet, but he had just stumbled upon one of the greatest medical discoveries of all time: penicillin. This accidental antibiotic would go on to save millions of lives. But Fleming's story isn't only one of its kind. Throughout history, discoveries have come about in different ways. Sometimes through happy accidents, like Fleming's. Other times, they arrive in a flash of insight, a Eureka moment where everything suddenly clicks. And in other cases, breakthroughs aren't found by chance or sudden realization, but through painstaking work, analyzing patterns, testing theories, and relentlessly pushing forward until the pieces finally fall into place. So how exactly do these paths to discovery unfold? Discovery. It can come about in many ways, but there are primarily three. Accidental discoveries, which require luck. Eureka discoveries, which require creativity. And brute force discoveries, which require effort. All three of these require other things as well. For example, even if you get lucky, you will still require a strong set of critical thinking skills to make any substantive scientific discoveries. However, of these three, the first two are almost impossible to replicate. As a method, accidental discoveries can't be taught, because luck can't be taught. It's a matter of unfolding circumstances surrounding the discoverer, more so than the traits of the discoverer themselves. Though, it is worth mentioning the old Louis Pasteur quote, "Chance favors the prepared mind." The method of Eureka discoveries also cannot be taught, because it demands deep creativity. Of course, like all three of these methods, Eureka discoveries also require good critical thinking skills, and may take time to take place. The real barrier, however, is creativity. Creativity cannot be taught. It can be nurtured through practice, or it can decay over time. But creativity is simply too general of a quality to be isolated to concrete steps. There is no such act of being creative. When we say that someone is being creative, what we mean is that someone is expressing their creativity through the art of blank. There is certainly a certain degree that knowledge and skill play a role in creativity. For example, knowing how to use a paintbrush can enable you to better express your creativity through the art of painting. But the thing that got better is your painting skills, not your creativity. And certainly it took a great amount of knowledge and creativity for Einstein to come up with his theory of relativity, and that knowledge can be taught, but the pure creative essence itself cannot. It can only be nurtured through practice or stimulated through exercises like lateral thinking techniques and cognitive restructuring. And that leaves brute force discoveries. When I say brute force, I don't mean violence. These types of discoveries come about by forcing them into existence through copious effort, such as Thomas Edison's invention of the light bulb. Effort cannot be explicitly taught, but it can be instilled and inspired. This method of discovery can be taught implicitly through such a process of inspiration. But effort alone is not enough. Effort alone would have us stuck reinventing the wheel perpetually. But when inspiration is combined with the right knowledge and skills,
Lee has only his Tai Jutsu to rely on.
All right, Lee, take him off.
Basic training equipment.
it can unravel even the strangest of mysteries. So how can we learn to brute force our discoveries? Inspiration is something that you have to find for yourself. I can't tell you what inspires you. That's for you to determine. But if you have that inspiration, then having the knowledge and skills can enable you to channel that inspiration into effort and produce brute force discoveries of your own. So let's go through a method of brute forcing a discovery and see what it's like. Okay, I'm gonna give the simplest practical scenario, avoiding any messy math or calculus to make this as understandable as possible. Suppose that we don't know the relationship between height and time for a 1D projectile. But suppose we know that the acceleration is constant, the initial height of the projectile is 15, and the initial velocity is 10. And we have the following data of height versus time. If we don't know the relationship between h of t and t, how might we go about discovering it? Before we even get started, we should add another column to our table to manipulate our variables. Let this column be represented by a modified value of t called t star. For now, we'll say that t star equals t. Then our first step is to match our start and our end point. Since our start is at h of 0 equals 15, let's try the most basic step of adding our initial height, 15, to our independent variable t. That corrects our starting point, but to fix our ending point, we need to alter our manipulated independent variable t star further. But how? We already added 15 to it. If we add or subtract anymore, then we're just going to keep moving around our starting point, which is bad because our starting point is already correct. Well, the smallest change we could make would be to change it from t star equals t plus 15 to t star equals a times t plus 15. But what value should we choose a to be? Well, if we want our endpoint to match, then we probably want to make sure that whatever value of a that we choose ensures that h of 3 equals 0. Therefore, we can solve for a. We find that a equals -5. Now let's adjust our table and graph. And what do you know? Our endpoints match. But you'll notice that our manipulated independent variable t star, plotted against our original values for t, only forms a straight line. Whereas our data for h of t versus t is more curved than that. And so the next step is to figure out how to match the points in the middle, get that curved behavior. But how? We already added by a constant and incorporated a coefficient for our variable. We can't do either of those two things without messing up our start and end points. How do we match the curvy behavior of the points in the middle? Well, there is something left, something that we don't normally write out, but is also present in our formulation of the manipulated independent variable of t star. Here we are working with a first-order equation, also known as a linear equation, because it is a straight line. By increasing the order of our formulation of our manipulated variable t star, we can add curvature. So let's try it. And our data becomes, well, that certainly gave us some curvature, and our starting point is still correct, but the middle points still aren't accurate, and our end point is off now too. This means we need to make another adjustment to t star. But what? If we change 15, then our starting point is wrong. And if we look at the differences between our numbers, they appear to be growing, not increasing by a constant amount. So changing -5 to a different number doesn't seem like it will really help either. How about we try adding in another term to our equation for t star? If we include the b times t term, then when t equals 0, bt equals 0. Meaning it doesn't affect our starting point, but it does affect our endpoint, since when t is greater than 0, then bt is greater than 0, supposing b is greater than 0. The only question is, what value of b should we choose? Well, if the last point that we want to ensure is correct is our endpoint, let's try using that. If h of 3 equals 0, what we want is that t star of 3 equals 0. So let's plug that into our equation for t star and solve it. And we find that b equals 10. Nice. Let's now incorporate that into our data and graphs. And what do you know? Our data matches perfectly. In fact, if we were to plot h of t versus t star, we would find that our graph would have the relationship h of t equals t star, which is a linear relationship with a slope of 1, which is exactly what we see. This process of manipulating variables to form a straight line between h of t and t star is called linearization. And it is the most simple way of brute force discovering a mathematical relationship for our data. But how do we know if this relationship that we found is a true scientific relationship? First, let's make sure that our mathematical relationship is even mathematically accurate. How do we know that t star really does accurately represent the height h of t? Well, we can do some statistics to determine our determination coefficient, r squared. Whereas r squared is the determination coefficient, when r squared equals 1, our relationship perfectly matches the model mathematically, and when r squared equals 0, our model does not match our data at all. Sigma is an operator that means the sum of. H of t is our observed values from the data points for the height in terms of time. T star is our calculated values based on our generated graph of t star versus t. H of t with a bar over it is the mean value of our observed values, h of t. I won't bore you with the details, but in our scenario, our data matches perfectly, and indeed we can calculate it out to find that r squared equals 1, meaning our model is a perfect fit. Let's go ahead and graph our equation for t star. You'll notice that in our equation for t star, that 15 happens to be our given value for the initial height, and 10 happens to be our given value for the initial velocity. But what about this -5? Let's assume that t star does represent h of t. Then, mathematically, the general form of this equation would be, but we want to know the scientific relationship. Well, let's change the variables we're using what we know about where they come from. Whereas t is the elapsed duration of time, h of t is the height as a function of the time, h naught, or h sub 0, is the initial height, and v naught, or v sub 0, is the initial velocity. To be sure that this is scientifically true, we would need to experiment with different values of the initial height and initial velocity until we are certain that they belong in our equation, and weren't just coincidentally the proper values. But if we do that, we would find that even for different values of our initial height and initial velocity, our value of A would not change. So what's going on with A? What does it represent? Where does this value of -5 come from? To determine that, we need more information. We could devise other experiments to flesh out our value of A, but to save some time, let's take advantage of hindsight. A quick Google search might tell you that the acceleration due to gravity on Earth is 10 meters per second squared. Wait a second here. -5 is equal to -1/2 times g, or the acceleration due to gravity on Earth. But why? The negative sign is the easiest to explain. If the direction of our initial velocity and initial height are pointed upwards, and that direction is positive, then since gravity pulls in the opposite direction, then the direction of gravity must be negative. That makes sense, but what about this 1/2? The truth is that I've told you a small white lie. The acceleration due to gravity on Earth is not equal to 10 meters per second. The acceleration due to gravity on Earth is actually 9.8 meters per second squared. However, our mathematical model fit our data perfectly, and so we would be justified to be pretty confident that our general mathematical form fits the general trend. This means that it can't be a rounding error or a problem in our calculations. It seems as though our actual data itself has some systematic inaccuracies that have caused the model we found to differ from reality. In the real world, this problem is typically even worse, because some errors are not systematic, they're random. You can't predict what direction they're going to be, and you can't expect them to bias each data point in the same way as the other data points. So how do you get around this problem? With enough effort, you can try to identify and solve the causes of your errors, then redo the experiment over and over again, and average your resulting value of A to make a good guess. But random errors will ensure that it will never be perfect. Additionally, this is not the only way that we can connect the dots. To the extent that our data is correct, there is another inescapable factor of luck. How do we know that we shouldn't be connecting the dots this way? The fact that the simplest consecutive manipulations matched T-star exactly is a fairly lucky situation. In the real world, you will typically not find an R² value of 1 so easily. However, there is another way, other than linearization, to make this brute force discovery. This equation for height can be found alternatively by using calculus. I'll spare you the details, but if you learn calculus, all you would need to know is that the acceleration is constant in our scenario, and I promise that you will not only arrive at this equation, but you will be sure that this equation is correct based on our given information. Without calculus, you would need luck to get errorless data in the first place, but you would also need to have a Eureka moment, where you intuitively or deductively realize our equation for the height as a function of time, and furthermore that A equals -1/2 g. But having knowledge of calculus enables you to brute force discover this relationship explicitly, without having to make a million graphs, and without all of the guesswork involved in linearization. Discovery is never a one-size-fits-all process. Whether it's the lucky break of an accidental discovery, the flash of insight in a Eureka moment, or the persistence of brute force. All methods require a blend of knowledge, creativity, effort, and a dash of luck. Brute force, in particular, shows us that with enough determination and knowledge, we can uncover the patterns that underlie reality. This exploration into discovery shows us that it is true that knowledge is among the most powerful of weapons, if you make the effort of wielding it. Thanks for watching.